All right, guys, so welcome. This is our first video on our study of the third unit, which starts with magnetism. So this chapter, chapter 24, focuses on magnetism, magnetic field, and magnetic force. So you guys are probably familiar with magnets a little bit. I'm not sure how much experience you've had playing with magnets at some point, but you kind of know how they work. So this is just a brief description of that. So most of the time when we talk about magnets, we talk about bar magnets. So a bar magnet's just like a rectangular magnet like you see in this setup. And one end of the magnet is considered to be north and the other end is considered to be south. So this is very similar in the nature of their behavior and the magnetic force between them. It's similar to electrical charges. So if you remember electrical charges, we had opposites attract and likes repel. Basically the same rules apply here with magnetic poles. So if you have two similar or like poles, so a north end and a north end, or a south end and a south end, then those two magnets will exert a force on each other that tries to repel, or a repulsive force. And if you have opposite poles, so like a north and a south end, they will attract. So that's the basic idea of how magnetic force works between two bar magnets. And just we're going to talk about magnetism a little bit as well, but magnetic objects versus non-magnetic objects, you probably don't deal with that many magnetic objects in your everyday life. So let me kind of try to explain what's going on with what creates or makes something magnetic and what's something that why things aren't magnetic. So if you look at this diagram over here, this is just a piece of a material. And we already talked about electrons are matter and they're in every single object that's made of matter. And electrons are moving charges. And movements of electrical charges will create magnetic fields. But in most objects and normal materials, electrons are randomly arranged. So there is no proper alignment. So they have what happens is that motion of the electron and the orientation of that creates a field in a certain direction. And in chemistry class, they define that as common or as spin or magnetic moment, and they describe it as up or down. You don't have to really worry about that. But basically what happens is, if you imagine these are like the magnetic fields created by these like bluish electrons, they're all in different directions. So there is no kind of set direction for all those individual magnetic fields. So when you add them all up, they just cancel each other out. So basically that's why things are non-magnetic, because they don't have a set orientation for their electrons. But in some materials that are magnetic, the electrons have a common spin or common magnetic moment, and the fields all align and join together, and they create this like net magnetic field. So we have all the arrows in here, which represent the magnetic fields, pointing in the same direction. So maybe this end of the object is south and this end is north. So that's essentially what it is. That's what makes something magnetic. Is if the electrons are all moving in the same direction and they create a common direction for the magnetic field. Now, there are other objects that become magnetic when they're put in a magnetic field, and that's because the magnetic field that it's put into aligns all those electrons in a common direction, and that's why it becomes magnetic. So magnets essentially have these electrons, and they're all going the same direct, like they're all moving in the same direction, which creates a common magnetic field. So that's the nature of how magnetism occurs in different materials and doesn't occur in other ones. We were talking about magnetic fields. A magnetic field is similar to an electric field. So we studied electric fields, and we talked about kind of it's the direction on which an electrical force would act on a charge. With magnetic fields, it's the direction that a magnetic force would act on a magnetic object. So if we have a bar magnet here, it creates a field around it. So if you look at this picture, so the symbol for a magnetic field is B, capital B, and the unit for it is a Tesla, which is a Newton per Coulomb meter per second. And this is a diagram for North Pole. The electric field lines leave the North Pole and enter the South. So that's sort of similar to what we had with positives and negatives. So it's a similar analogy. But in a magnetic object, there's also a field. So that field also goes in that same direction, so it leaves positives and goes towards the negatives. So that would be kind of the direction of the magnetic field. So all these lines are looping around, and if you put a magnetic object there, then you would see the effect, or it would feel the electric force in the direction of those field lines. So I have some more pictures here to help you kind of try to understand. Another idea that sometimes happens, so we are going to start studying magnetic fields and their effects on charges and wires, and we're going to have to get into three-dimensional kind of ideas. So sometimes we'll have field lines that are directed into or out of a page. So what I mean by that is this circle represents a point where the field would be coming at you. So it would be coming like out of the screen towards your face. And if you see an X, that would be a magnetic field line going away from you. So that's going away from you as the X. It's sort of like a bow and arrow kind of idea. So if we had a bow and arrow, and you imagine kind of the arrow is set up to look like that. So that's a really bad arrow. But the tip of the arrow is maybe at this end, and the back of the arrow, I'll just write B for back, is at that end. If you imagine the arrow was being shot at you, you would just see the tip of the arrow. So you would see that dot coming at you, the point coming at you. So that's what the circle means. And if it was being shot away from you, you would see the tail feathers kind of the arrow, and that's what the X represents. When I have a picture of a toy here, so I don't know if you guys are familiar with this. It's called a Woolly Willy. Basically, you have a magnet, and you have these magnetic shavings, and you can kind of move the magnetic shavings onto the face, and make them have different facial hair or a beard, whatever it might be. So, but the magnetic force moves those magnetic filings. And those filings show the direction of the magnetic field if you put it in there. So we're going to look at kind of some pictures that go along with that. So this is the bar magnet. The field starts on the north end, which is the red end here. The south end is the white end. And these are the little filings that are going around it. So if you look at this pattern of those iron filings going around the magnet, you can see kind of the same pattern that you have from the north going towards the south end. As you get further away, the field gets weaker, so you don't see those filings moving as much, but as you're close, you see them affected a lot by it. Another kind of setup, we have a north end and a south end, and again, the field line should go from the north towards the south, and it's going to, and you can see this pattern in these filings. So that's why I brought up that toy, because it kind of shows you that. And then we also have this pattern from the north and to the south, and you can see kind of the directions of those fields and how they're influenced. If we had two north ends or two like ends towards each other, you can see in the middle there is no magnetic field, because those field lines, similar to electric field lines, they can't cross. They get close together, and they're closer together, they're stronger. When they're further apart, they're weaker. So it's a lot of similar ideas that we talked about with electric field. We're just talking about magnetic field, but they are different. So magnetic fields come from magnets, electric fields come from charges. So very different ideas so far. Okay, so hopefully that drawing or looking at electric fields makes sense. So let's try a question or two to see how we're doing with it. Okay, so in this first question, it says a compass is placed at the black dot. And a compass is basically just a magnetic field indicator. So it's like a magnetic material. And if we put at this black dot, we put a compass, how would it orient itself? So again, the north end is the kind of shaded in, and the white end is the south pole. So if you thought about this, I'm going to give you a second to answer. Which one of these choices, A, B, C, D, or E, would show you where the compass would point in this setup? So if I put the compass here, how would the compass spin? So we're looking at kind of the triangle here in the compass. So again, the shaded in area is kind of the north end, and the south end is the white end of the compass. So I'll let you pick that answer now. And the correct answer is answer B. So the south end would be attracted to the north end. The north end would be repelled from the north end, because opposites attract and likes repel. So it would spin around, and it would look like this if you had it. Okay. Another one So if we had this setup with these two magnets, so south and north on the top magnet and north and south on the bottom, how would the compass reorient itself again? So let me give you a second to do that. No, and I didn't have the answer covered up. It is D. It's the answer D. So it makes sense because, again, the south end is going to be attracted to the north, and the north is going to be attracted towards the south. So it's pretty straightforward. It's just showing you kind of the direction that the magnetic field would be directed. All right. So now we're going to get into, we've talked about magnetic field a little bit. We'll come back to them in a little bit. But we want to talk about how magnetic fields affect charges. So because we talked about like magnetism comes from moving charges, those moving electrons create magnetic fields. If you put a moving charge in a magnetic field, then there's going to be something magnetic affecting something magnetic, so you have a magnetic force. So forces on a charge in a magnetic field are described by this equation. So first off, FB is the magnetic force, so force magnetic for B, is equal to QVB sine theta. So Q is the charge, V is the velocity of the charge, B is the strength of the magnetic field, and then theta is the angle between the magnetic field and the velocity vector. So if I drew something like, let's say I was drawing magnetic field lines that were like this, so I'll label that B for the magnetic field, and I had some charge, which I'll say is Q. And let's say the charge is moving at some velocity V. All right. The angle between those two things would be theta. So those are the ideas that we're talking about. So if I wanted to solve for the equation, I would need to know the values for all these numbers here. But I would just plug in and get the answer for the magnitude or the size of that magnetic force that's acting on it. So it's really kind of just multiplying three numbers, and then you take the sine of the angle between them. All right. So that is fairly straightforward. I don't think the math is so hard in this part, but the idea of how, like the directional part, that's where it gets a little confusing. So we're going to figure out the direction of the magnetic force experienced by a charge using this rule, which is called the right-hand rule. So as it makes sense, the right-hand rule makes you use your right hand. And this is right-hand rule number one. We'll talk about right-hand rule number two later on. But essentially what you do is you use your hand. So you just put your hand flat, kind of like in the picture that's shown there. And your thumb represents the velocity direction. So your thumb, wherever your thumb is pointing, is where the velocity is. Your fingers are pointing in the direction of the magnetic field. And then the palm of your hand would push in the direction of the force. So if you look at this in this example, if the velocity is going kind of in that direction and the fingers are going in that direction, then the palm is facing up and it's open, and that's the way the electric force would act on the charge. So the charge, if it was moving kind of in that direction and the field was going in the direction this way, and again, it's three-dimensional, so this is where it gets a little tricky, the magnetic force would be pointing upward. So the charge would get pushed up as it is moving in that direction, so it would kind of loop around, right? And one really important idea of this rule, and we're going to practice this so you'll get better at it. One important idea of this rule is it assumes that the charge is positive, all right? So that's how it would affect a positive charge. A negative just does the exact opposite, so it goes the opposite direction of your palm, or if you wanted to, you could use your left hand and it would do the same thing. But I generally just say use your right hand, and if it's negative, it goes the opposite way. So that's the way I would describe it. All right, so let's try a scenario here and try to figure out what's going on. So it says the direction of the magnetic force on the proton is, so protons are positive, so we're going to use the right-hand rule. And our velocity is going up. So we're going to put our thumb in that direction. And then we need to orient our hand. So our thumb should be pointing up towards the top of the screen. We need to orient our hand in the direction that the magnetic field is acting on the charge. So if you follow this north, it kind of loops around to the south. So kind of I would have a line that would look like this. So I would assume the magnetic field is kind of trying to go that way. So if that's B, I'm going to put my fingers in that direction where the blue arrow is going for B. My thumb is going to go in the direction of V. And then you have to figure out which way your palm is trying to push the proton. So if you describe that, which of these would that be? And it's going to try to push the proton kind of directed exactly towards you or out of the screen. So again, it's a three-dimensional idea. So the force is actually causing the velocity to change direction. It's not causing it to speed up or slow down. So so that's another kind of conceptual question. We got another one here, so let you try this one. So it says which magnetic field causes the observed force. So so this is a little bit different. It says the force is coming out of the screen, so the force is coming towards you. Take note of what charge this is. So it's not a positive charge in this one; it's a negative. And then the velocity is still directed kind of down and to the left. So so you have to think about, okay, I want the force to come out of the screen. I'm trying to figure out which way I need my fingers to point in order for that to work. So so you can, again, use your left hand if you want to think about it that way, or you can use your right hand. It's the back of your right hand because it's the negative charge. So if I put my thumb kind of down and to the left, and my palm is going to be, if it's a positive, it would push into the screen, but it's a negative, so it's going to push out. If you look at where your fingers are pointing, your fingers should be oriented kind of in the direction of C here. So C is the correct answer. All right, so these right-hand rule ones are a little bit tricky. And that's for the right-hand rule one is for forces. So it's the force acting on a moving charge. Again, just to go back to the equation a little bit, the magnetic field is zero. I'm sorry, if the magnetic field is zero, so if there's no magnetic field, there's no magnetic force. That makes sense. Another thing is if there's no charge, there's not going to be any force. So if it's like a neutron, there's no charge on a neutron. Neutron's moving through that field. It's not going to be deflected at all. It's not going to make it change direction. The velocity also has to be a number, so it has to be moving. If you just have a stationary charge, the magnetic force is going to be zero because it's not moving. So those are the three things that you have to be. And then the angle between Q and V, I'm sorry, between the velocity of the charge and the magnetic field has to be some number. So if you put in sine of 0 degrees, you get 0. So they can't be parallel to each other, or anti-parallel. The velocity has to be going at some angle compared to the field. All right. So we also talk about wires and forces on current carrying wires. So as we described the force on moving charges, in a wire, the current in a wire is just the sum of many charges moving. So it's got a force. If it's in a magnetic field, it's going to have a force acting on it as well. So so the equation for that, FB, is equal to ILB sine theta. So I is the current, L is the length of the wire that's in the magnetic field, and then B is the magnetic field strength. Again, it's based on the sine of the angle. And the right-hand rule is exactly the same. It's just this time, instead of having your thumb be the velocity, your thumb is the current. So your thumb points in the direction of current, your fingers point in the direction of the field, and then your palm pushes in the direction of the force. For a current carrying wire, there is no reverse direction. So like your thumb is just always the direction that the charge goes. So you don't have to worry about like, is it positive or negative? It's just your thumb points in the direction of the current. So if we look at this example over here, we have our wire directed up and down from the top of the page to the bottom of the page. The electric field is the X's, so that's your fingers, and that's pointing away from you. So the current is going up towards the top of the page. Your fingers are pointing away from you. If you hold your right hand in that orientation, your palm would push to the left. So that's why these red arrows are representing the electric force on that wire when it's in that field. All right. So so that's another setup. Okay. So let's try this one. This one's a little trickier, but I think you'll get it. So it says the horizontal wire can be levitated, which means float, or held up against the force of gravity if the current in the wire is in which direction. So we're trying to figure out that. So gravity is trying to pull this wire down, and we're going to use the current in the wire and the magnetic field to hold it up. So what way do we need the force to go? We need our force to be directed up. So our palm should be pointing up towards the top of the page. And then our field is our fingers. So our fingers are pointing into the screen or away from us. So if you look at your thumb is the current. So it looks like our current is going to go from left to right this way, which is B. So if I draw that in, if I draw that current in going this way, if that's I, so I and B is into the screen, and then your palm points up. So that's good. So we'd have this magnetic force going up, FB. and we have the FG going down. And if it's levitating, that just means that in your free body diagram, they are balanced. Okay. All right, so we're almost done. We're going to talk about another scenario. So we talked about magnetic forces and we calculated them. The next thing we're going to talk about is because we have current in a wire, that current is creating a magnetic field. So a moving charge creates a magnetic field, just like a moving charge like an electron is what's creating a magnetic field. So we want to figure out how much magnetic field is created by a wire. So this is the magnitude of a magnetic field created by a current carrying wire. The equation for it here is B, which is the magnetic field strength, is equal to U naught, which is something called the permeability of free space. It's just another constant. It's this number. So 4 pi times 10 to the negative 7th Tesla meters per amps. You can also describe it, I think it's like I got it here in the book, 1.26 times 10 to the negative 6th. It's the same thing. It's just 4 pi, and they replaced it with a number. So that's a constant. I is the amount of current that's going through the wire, and then you divide it by 2 pi r. Now, r is the distance from the wire. So if this is my wire, so if I'm drawing a wire here, and we have some current going through it, we need to measure the field at a position. So if we measure it here or here where I'm putting these X's, that is kind of the distance R. So if this is X3 maybe, that would be R3. So it's just like how far the position we're measuring it at is from the wire itself. So that's what R represents. And if you look at this, R is in the denominator, B is in the numerator, so they are indirectly proportional. So the further you get away, the weaker the magnetic field. That's another idea that kind of just logically makes sense. So if you're further away from the wire, it's going to have less of an effect on you. All right. That's what that's saying here. So the magnetic field creates what's called a current, and it creates a loop of field that actually circles the wire. So this is another right-hand rule that we're going to use. This is right-hand rule number 2. The way you do this one's easier. You just grab the wire and you make sure your thumb is pointing in the direction of the current. And the way your fingers of your right hand curl around the wire is the direction of the magnetic field loop. So if in this picture here, the current is directed upward, so I is going up. And as I grab that wire, if you want to use a pencil or a pen to help you visualize this, if you grab your pencil or pen and you have your thumb pointing up towards the top, your fingers curl around the pencil or pen in the direction of the magnetic field. So that's an easy way just to use a physical object, and then you can rotate it however you need to. All right. So a couple more conceptual questions and we're done with the first video. So it says, compared to the magnetic field at point A, which is 2 centimeters away, the magnetic field at point B is what? So B, it's actually 4 centimeters away. So these are your options. We're going to be able to tell, so it's not going to be E. So we need to figure out, okay, what's the difference between these two ideas? So we have the same current. So again, the equation is B equals U naught I over 2 pi and then R. So U naught is a constant, I is the same for both of them, 2 pi is a constant. So it's really just R that's making an impact. And if we compare the separation for A versus the separation to B, there is as B is further away, so it's going to be less. And how much further away is twice. So if it's twice the distance, it's going to be half. So it's not going to be C or D. And now we need to figure out the direction. So when you're figuring out the direction, you grab and use your right-hand rule number 2. So if we grab that wire and we have our fingers loop around the wire, at point A, I would say the field is coming out of the page. So I would see a dot here everywhere on this side of the wire. So these would be dots, because remember, dots are coming at you. So these red dots represent the magnetic field at a distance of 2 centimeters away. If we grab the wire and you think about your fingers kind of on the right side of the wire, it's going to be going in. So these are all X's over here. So these would be X's. So X's and dots are opposite directions. So it's going to be half as strong and they're going to be in opposite directions. And we just established the directions that they should be. Okay. I think this is our last one. Yep. So our last one here, just kind of working with this equation again, it says the magnetic field at point P is 0. So we have 0 here. And we want to know what is the magnitude and direction of the current in the lower wire. So we're going to measure the magnetic field at this point, and we're going to figure out how much current has to go through this lower wire. So we have this wire, and we can kind of figure out a couple ideas here. So if we're doing our equation B, and that's what it says here. So what is the magnetic field created at a point P by the upper wire? B equals the same equation that we just had. So U naught I over 2 pi r. And I'm going to plug into that. So U naught is the constant, so that's 4 pi times 10 to the negative 7. It's just a constant. I is 10. And then we're going to divide that by 2 pi times r. So we need to figure out what r is for the upper wire. So if it's 4 between the wires and it's another 4 to point P, that's going to be 8 centimeters, which is 0.08 meters. Okay, so I can cancel out the 2 pi and 4 pi and just get 2 on top. So this would be like 20 times 10 to the negative 7 divided by 0.08. So that value is something like 2.5 times 10 to the negative 5th Tesla. So that's the magnetic field strength from the upper wire at this point. And let's think about which way that field is going to be going. So is it directed into the page or out of the page? So if we grab that wire, so it's that horizontal wire, and I'm looping it around. So if you hold your pencil horizontally and you put your thumb going to the right and you loop your fingers around, above the pencil, your fingers are pointing towards you, and below the pencil, your fingers are pointing into the page or away from you. So when that's happening, that means we have an X here for the upper wire. All right, so that's going into the page. So we need to cancel that out. So in order to cancel it out, we need the exact same amount. So this number needs to be created in the opposite direction for I, for the lower wire. So if I make a different color and call this L for lower, the same field strength has to be there, but it has to be coming out of the page. So this out and in would cancel each other out, and there would be no magnetic field. So in order for that to happen, we need to make it so that we can make our fingers come towards us as we orient our hands. So again, if you take your pencil and you grab it so that your fingers are curling or pointing at you underneath the pencil, your thumb points to the left there. So the current in the lower wire has to go to the left. So that's the direction of the current. And now we need to figure out, okay, how much current do we need? So if you think about this, if we look at this distance, we could do this math. I think it's easier just to like rationalize it and use some logic. So it's 4 centimeters away, which is half the distance. So if we have half the distance, we need half the current because we got to make it proportional. So if this becomes 0.04 on the bottom, to keep it the same number, it would have to be 5 amps on top. And if you check the 2 times 10 to the negative 7th times 5 divided by negative 4, you will get the same number that we did for the upper wire for the lower wire. Okay, so that's the lower and that was the upper. Okay, so that's really a lot of the different ideas that we've talked about. This is about a half-hour video, so that's not too bad. But again, we kind of established what how magnets behave when you put a magnet towards another magnet. We talked about magnetic force on charges, moving charges on wires. We talked about the fields created by wires, and we used the right-hand rule. So right-hand rule 1 is the one for forces, which is the first one we learned, where you put your thumb in the direction of the velocity or current, your fingers are in the direction of the field, and your palm pushes in the direction of the force. And then for magnetic field created by a wire, that's what we, a current carrying wire, that's what we just did. That's right-hand rule tool, where you grab the wire and make your thumb point in the direction of the current and your fingers curl in the direction of the field, okay, in those loops. So, so that's the first part of the ideas on magnetism. The next video will be for chapter 25, and that's going to deal with different ideas called induction and inducing currents. So Have a good one.